Hey everyone, we're back and we are in chapter 6, lesson 1. So, I have some good news for everyone. We're definitely winding down this school year. And for that reason, we have been working hard through chapter 4. No chapter test. We're going to leave it with the two quizzes from the first part of the chapter and from the second part of the chapter. So, we just took a quiz on lessons 4, 5, 4, 6, and 4, 7. And hey, you got to use your notes and your trig wheel for that. So hopefully you did well. And more good news, we're actually going to blow right past chapter 5 and going to end up in chapter 6. I can't speak for everyone. Most students say chapter 6 is a little bit, at least lighter than chapter 4. We dug real deep in chapter 4 with some heavy duty stuff, but this material will be maybe just a little bit lighter. Some students think a little bit easier, which would be great. And maybe one of the best bits of news for everyone, we're still going to consider angles, but we're going back to the old way that we considered angles in degrees. And so for some of you that took a while to get used to radians or were struggling through that, we're going to work with degrees. Now, one significant thing, because we're going to use our calculators, we're going to need to make sure that our calculators are set for degrees. And it starts to get a little tricky on things like final exams. If some of the questions are in radians and some of them are in degrees, we're just going to have to be real careful. I'll do my best to give you reminders, but right now, even as you're watching this and getting ready, we're going to do some examples together. Get your calculators and get them set to degrees. That's going to help us a lot. In lessons 6.1 and 6.2, what we're going to do is something actually really important in a lot of industry. In real life, it has some good application, but it comes down to kind of pictures, to triangles. And we're going to do what we call solving a triangle. To solve a triangle means that you can identify the length of each side of the triangle and the measure of each angle of the triangle, given only some of those pieces of information. Okay. And so this was easier when we had right triangles, because right triangles, we can use the Pythagorean theorem if we know two sides and not a third side. We also had the opportunity, we learned in the last chapter, to use SOHCAHTOA, and we could use sine ratios and cosine ratios and tangent ratios, because that worked for right triangles only. Well, it turns out our knowledge of sine and of cosine are going to benefit us, and there are things that we can do when we have what we call an oblique triangle. That's a triangle that's not a right triangle. And so that's the goal in these next couple of lessons. And today we're going to look to solve triangles that are not right triangles using something extra that we're going to learn about sine and something we can do using sines. And so I just want to remind you, as we solve triangles, we're not going to know information. And so I tend to just draw a triangle any way I want, knowing that there's mystery information. There's sides I don't know the length of. There's angles that I don't know. I don't know if I'm drawing them correct or incorrect, but I just generally draw some sort of triangle that doesn't look like a right triangle. And what I want to remind you is that we often label triangles by it. It's three angles. We call them A, B, and C. Now, C was always the hypotenuse of a right triangle. And some people say, you know what, even if it's not a right triangle, like this angle almost looks like a right angle, they say, I like C to be my longest side. Pretty much it doesn't matter. We can pick any angle as A, B, and C. So the sides of the triangle will be the lowercase letters of the angle that they are opposite. So again, normally angle C would be my right angle because the hypotenuse would be lowercase c, side lowercase c, but I've switched it up a little bit. And so This side, which clearly looks like the longest side of the triangle, I'm going to call side B. This is side lowercase c, and this is side A. So for this triangle to be considered solved, I'm going to be able to tell you the length of side A, side B, side C, and the measures of angles A, B, and C. And I'm going to start with some information that they're given, and we're going to use something today that's known as the law of sines. And hopefully you've got your note page, so you've taken a look at this already. But what we can show for any triangle, we could take the time to prove this, but we're not. Hopefully you'll just take my word for it, is that the ratio of side A, the length of side A to the sine of its opposite angle, is equal to the ratio of this side to this sine is equal to this side to this sine. So the way we write that is A over sine angle A is equal to side B over sine B, which is also equal to C over sine C. Okay, and some textbooks will just flip these. They'll say sine A over A equals sine B over B equals sine C over C. It turns out that's the same exact thing, but this is going to be really valuable to us. This is for any triangle. It's not just right triangles. When I did sines with SOHCAHTOA, opposite over hypotenuse, had to have a right triangle. Turns out these ratios are good for any triangle, and so we will use them to solve triangles. Now, a quick visit back to our geometry days. Maybe some of you did this, maybe some didn't in geometry, maybe you remember it or you don't. But we used to have to prove that one triangle was congruent to another triangle. And the way we proved it was, rather than have to show every single piece, every side and every angle, it turns out that if I just had a few of those bits of information, it had to be that these two triangles were congruent. And so you learn things like angle side angle and angle angle side, and side angle side and side side side. All of those were legitimate ways to prove two triangles congruent. There was one that wasn't enough information, and we'll get to that one in a second as we deal with some of these law of sine questions. But I want to do a couple of examples with you where if we had two angles and a side of the triangle, we can use the law of cosines and we can solve for that triangle. So let's take a look at this. I'll use what I have drawn on the board here, and I'm going to give you some information. So I'm told that angle C is 63 degrees. I'll write it on the side here. I might label it on the triangle too. So angle C is 63 degrees. I'm told that angle A is 46 degrees. And I am also told that side C is 56 inches. So again, I know two angles and I know a side, and that's enough information for me to say there's only one possibility for this triangle. And so there's only one possible answer for side B and angle B and side A. And we're going to put the law of sines to use to figure some of this out. All right. First of all, I want you to realize, I think you probably already do, that when they say we gave you two angles of the triangle, really we have three, right? When they only give us two, one of the things that you need to remember from your geometry days is that all of the angles of a triangle add up to 180. So we can easily add these two angles up, subtract from 180 to find the measure of angle B. And so we would find, I think You can do the math on your own, but angle B is 71 degrees. Because 71 plus 63 plus 46 has to add up to 180. So add the two sides that you know, subtract that number from 180, and you know the third angle. So at this point, trying to solve this triangle, I now have all three angles listed. I have one side. I need to get the other two sides, and I can use the law of sines where I can't use the Pythagorean theorem. It's not a right triangle, or at least I don't know that it is. I can't use SOHCAHTOA. I can use this information and the law of sines. And so really this is kind of like a multi-equation. I don't need all the pieces. For a second, let's take this part off and let's just do side A over sine A equals side B over sine B. And no, let's not use A and B because side C is actually the one I know. So side A over sine A equals side C over sine C. And the one I'm trying to calculate or find is side A. I know angle A, so I could find its sine. I know angle C, so I can find its sine. I know side C. And so at this point, some students like to plug in numbers right away. Let's plug in what I know. I'd love to do a little algebra. If I wanted to solve for A, if I wanted to get A all by itself, hopefully you guys would see I could multiply both sides of the equation by sine A. Okay, if I multiply by sine A, these would cancel out. And so I have A equals C times sine A over sine C. Okay, remember when we do sines, that's of the angles. That's a capital C. This is a lowercase c because it represents the side. And so side C is 56 inches times the sine of angle A, which is 46 degrees. Please be sure that you are set in degrees and not in radians. And that's divided by the sine of 63 degrees. All right. When it's all just multiplication and division, we shouldn't really have to worry about parentheses. Just want to be careful when we do our fractions. But when we work through it all, and you could be maybe punching that on the calculator right now. Turns out the length of side A is about 45.2 inches. So I now have three angles and two sides. To solve this triangle, all I need is the length of side B. And I'm going to do the law of sines again. Now, I will say we've got a couple of different options here. It's always best to work with exact numbers that you know. This side A is 45.2 inches. I rounded off the answer a little bit, but I know that side C I know exactly. So I'm going to say C over sine C equals B over sine B. Okay, that's using the law of sines. And again, some real quick algebra before I even plug in numbers. If I multiply both sides by sine B, these would cancel out, and I'd have side B, the side I'm looking for, equals sine B times C over sine C. That's a pretty simple algebra step. And I'll let you guys plug in and punch in those numbers. And hopefully you come up with side C is about 59.4 inches. And the question would be done now. The triangle is considered solved. We have all the sides and all of the angles. So the law of sines, and it would have been hard to teach that to you until you understood what sine meant and the sine ratio and all of the stuff we did in chapter 4. But now that you do, we can use a pretty simple law and a simple tool to be able to deal with triangles that are not right triangles. And it gives us a lot of power. And so that's solved. That's some of what your homework is going to be. This is a situation where we have two angles and a side, okay? And sometimes that can be given to us as angle, angle, side, or angle, side, angle. There's, I told you, side, angle, side. We can kind of come up with unique triangles, but that's something that we're going to save for the next lesson. I want to show you an issue where we might be given an angle and two sides, and the angle is not in between those sides. If it is in between those sides, we call that side, angle, side. And in the next lesson, we're going to learn how to deal with that. But if I have angle, side, side, okay, first of all, that abbreviation would get us into a lot of trouble. But here's why we can't say for sure exactly what we have going on. I'm going to give you a visual demonstration of angle, side, side. Right? I'm going to draw the side of a triangle. And I just made it go on forever because this is actually one of the sides I don't know. I do know this angle here. And so I know this angle. I give it some measure of degrees. Doesn't really matter. I'm just going to call it theta right now. It stands for some angle. And I know the length of this side. It's exactly this long. Okay. And I know the next side also. I know how long it is. That's all I know. This side runs along here because I gave you the exact angle, but I don't know where it ends. So I just drew it really long. And let's say that the third side, is this long. I have a piece of yarn here. And so I know the angle, I know one side, and I know another side, and I want to solve this triangle. And so I'm going to put this side, try to do this so you can see. If I put this side and I touch it right here, see if I can get out of the way, there I would have a triangle, and it should be solvable. But I want you to see this third side or this second side. I could take it and I could swing it over to here and touch it here, and I have another triangle. So it would work to have a triangle here, and it would work to have a triangle here. I could possibly have two different triangles. Or if I said the second side is this long, all right? And so I'm going to put that here. Well, it turns out it doesn't matter where I swing it. I can't even enclose a triangle. If I know that angle theta over there, and I know the side of the marker, this side here, and I know the third side is this long, I can't even make a triangle. It's impossible. There's no solutions. So when I have two sides and an angle that's not included or not in between them, then we have kind of an ambiguous case of the law of sines, and we have to explore a couple of different opportunities. And so I want to take a look at some of those real quick, and I'll set you free to doing some of your work. Let's say that we want to solve triangle ABC, and here's the information that they give us. Right, they tell us that angle A is 75 degrees. I think I want a better marker. Angle A is 75 degrees. Side A equals 51, and side B equals 71. They want us to solve this triangle again. Since I have missing pieces, I'm just going to draw any old triangle so I can visually see how some of this might work. Wow, that was bad. So I'm going to call this triangle ABC, and I label the sides opposite. And so this is what I know. This is 51. This is 71, and this is 75 degrees. So again, I have angle, side, side. I don't know for sure that I have any triangle that exists, or I may have one, or I may actually have two triangles that could exist. So let's do the law of sines. And the law of sines says A over sine A. So let's write 51 over sine 75 degrees equals B over sine of angle B. 71 over sine B. Now, this is a little trickier. The thing that I don't know is at the bottom of a fraction, I've got to do some multiplying and dividing to rearrange. This algebra part still gets some of you caught up. I have to get sine B, the thing I don't know. I have to get it to the top of a fraction. So I need to multiply it to bring it over here. Then I need to divide 51 to move that out to the other side, and multiply sine 75 to move that to the other side. I'll go slower when we do that in class if you're struggling with it, but it's essentially going to say this: sine of B equals 71 sine 75 over 51. All right. Now, I need to grab my calculator, and you guys can punch that along. I need to find my calculator. There it is. All right, so we're going to do, actually, I'm going to make sure I get into degrees. And we're going to do 71 times sine 75 divided by 51. And it turns out that according to this, the sine of B equals 1.82. So I know the sine of B. I want to find angle B. This is, maybe you remember back to the last section, this is an arc sine situation. This is find the angle whose sine is 1.82. The way I've moved that word sine to the other side is change it to an arc sine So this will say B equals arc sine 1.82. And some of you might have realized the catch already. We had these trick questions in the last section. It says find the angle whose sine is 1.82. I know I can ask my calculator, but I already know what my calculator is going to tell me because there are no angles that have a sine of 1.82. Sine never goes higher than 1. So this is undefined, and it's going to turn out I don't have any answer to this. It's not a triangle that can be created, right? If you can create a triangle, ABC, with these labeled sides and angles so that side B is 71, side A is 51, and angle A is 75. If you could create a triangle with those dimensions and actually make it be a legit triangle, I'll just straight up give you an A. You don't have to do any more work for the rest of the year because according to this, it's not possible. There's no way we could have a triangle with those dimensions because when I do arc sine 1.82, my calculator tells me error, that it can't exist. All right. And so we're going to do some problems where we know the angle and the side, angle, side, and we just have to explore. There may be just one answer. There may actually be two answers. You'll encounter some of those in your homework, or there may be that there's no answer. There's no triangle that would fit this information. All right. So I'll let you work on some of those. We can go over them in class. I want to show you one last thing. I'm not even sure I need to do an example because it's really quick and easy, but maybe you remember to find the area of a triangle. The formula for the area of a triangle is 1/2 base times height. And so one of the questions might be, if I kind of draw a triangle that looks like this, what do I mean by my base? Like I don't even have a piece that looks like a bottom piece. It's kind of turned funny ways. The thing is, when you do 1/2 base times height, you could pick any side as your base. Okay. I could pick this side AC as my base, but then when I say height, what I mean by height is what's the distance to the opposite side drawing something that's perpendicular. Okay. And so it becomes a little tricky figuring out what the height is. And so that works. Right triangles, it's really easy to do this because you do have a perpendicular angle or a right angle. But I get a little more confused when figuring out what the height is to come up with the area when it's this kind of triangle. Well, there's a pretty simple formula. And if we know the information that's given, we can find the area of a triangle. It's there on your notes, so I won't rewrite it. Area is 1/2 side A times side B times sine of angle C. Okay. In this case, this would be side A, and this would be side B. This would be side C. So it's 1/2 this side times the angle in between. And I can switch that formula up depending on what information I know. If I know this side and the angle in between, it's going to be 1/2 B times C times sine A. If I know this information over here, the area is going to be 1/2 A times C times sine B. So I wrote one formula in your notes. It says area equals 1/2 AB sine C, but you can add to that or write additionally 1/2 AC sine B or 1/2 BC sine A. Any of those will work, and we're just going to plug that information in, and we know the area of the triangle. And that was hard to do because of this whole perpendicular thing. When we didn't have right triangles. Right triangles were always a little bit simpler. Now we can do this kind of stuff with our knowledge of sine and with a pretty simple formula that we've been given. And so I'll let you practice some of those too to come up with the area of some triangles if we're given some key information. So the homework is there, listed page 690, 1 through 21, and 33 through 37. The odd questions from both segments. I will list it here in the assignment as well. And we'll get to talk about that in class early next week.